Jason, what are we talking about?
Today, we are going to be talking about formal verification and its fragility. The fragility of formal verification.
The fragility of formal verification. So maybe give us a pithy definition of formal verification.
How confident are you that lattice-based math ain't going to fail?
Not at all.
Right.
Right.
There it is. And so why are we confident in RSA and ECC?
I'd say the primary reason we're confident in RSA and ECC, the primary reason is just they have withstood the test of time. I think there absolutely have been people who have attempted formal proofs of their strength. But I think the real thing that makes us confident is that people aren't cracking them open.
Tim, we had Michaela Muska.
We did.
On this podcast a few times.
Mm-hmm.
And he talked about some of this. And we talked to Dr. Dustin Moody about this.
Mm-hmm.
And they all said, look, we need other forms of math because we can't be sure of anything. And this is really, why do we have to have diversification?
Right.
That was my exact question to Dustin.
Yeah.
Why do we need it? Tell me. And he said, it absolutely has to do with the fact that we need diversification. The need for diversification in the math in our cryptographic algorithms is because of this fragility in the formal verification process.
Right. Yeah. And some of this goes back to like some fundamental tenets of knowledge, like you can't prove a negative, right? So I can show you a proof that I have broken a cryptographic algorithm, and then it's definitive. But I can't show you a proof that nobody can break a cryptographic algorithm.
Tim,
right.
There's going to be 2 more podcasts coming out of this one.
Okay.
The number one is this. Did you know that AI has now officially been optimized to defeat ECC?
I think I saw a headline on this. I did not get a chance to read the article because I was doing something and then I forgot to go back. But I did see a headline on this.
Michaela Muska predicted this on our podcast.
Right.
And he was right.
Yep.
And now stay tuned. There's another podcast coming.
All right.
And number 2 is, I think, Tim, we did a very interesting episode recently where we talked about side oracle attacks.
Yes. I was going to come to this, but go ahead.
Part 2 is coming.
Yeah.
And part 2 is, I think we're going to have to call it the side chain crisis of PQC.
Okay. Yeah. We've seen that, haven't we? And connected to that, bringing it back to your original idea about formal verification, even hypothetically, let's pretend that I could sit and I could give you an unimpeachable mathematical proof that the algorithm was undefeatable under any circumstances, which I don't think you or I believe that's possible. But let's pretend it was. That wouldn't matter if implementation weaknesses still left the algorithm open to attack.
That's one class.
Right?
There's another class, Tim, that, with the RSA, we're dealing with integers.
Mm-hmm.
And with PQC lattice math, we're typically talking about big polynomial equations where it's not just integers. If there's a bug that presents itself as polynomial noise, for the lack of a better way of saying it, that noise generation might not break in a nice way where we can go, oh, PQC algorithm failure, it failed. There's a bug. We need to go fix it. That bug may unfortunately cause randomness to be less random. And that's essentially what the bug is. And there may be a blind spot to it. I'd almost say, Tim, that I'm going to push Michaela Muska's prediction one step further and say AI will not only be used as a cryptanalysis tool to break, it might be used as a cryptanalysis tool to determine, are our assumptions about PQC math true?
Sure. Right. What if they're not? Can we know that they are?
So the opposite, really truly the opposite of what we talked about earlier, which is AI being used in the hands of the adversary or the researchers to break things, it's also formal verification. And I won't call it, it's probably not the right word. It's not formal verification. It's verification.
Yeah, right.
And so how do you find all the blind spots?
Oh, yeah, right.
So I think, Tim...
And this ties to something we discussed when we talked about, very recently, we talked about principles. You had a list of like some basic principles of PKI. And one thing that you said that is that, I'm not sure what the word to look for is, but that novelty is bad, right?
Novelty is bad.
And this goes back to that, right? Because again, how did we start this whole conversation? Why are we confident in RSA? Because it's been around since 1978 and no one's beaten it.
It is not novel.
Right. It is very not novel, right? And we pointed out in that episode, and I'll just point it out again, the conundrum with PQC is that by definition, by the nature of what we're doing, it all must be novel.
It's true.
Right.
So there are many things in lattice math that are not novel.
Mm-hmm.
But Tim, there's leakiness. There is, anytime you try to do a formal verification, it proves the code is correct, but often it proves perhaps the logic is correct, but it doesn't prove the physics is correct.
Okay.
In other words,
Right.
that unexpected blind spot randomness.
Right.
And as the math becomes more complex, because we have to admit, RSA and ECC, I mean, give it to the average person and try to read that. That's some complex stuff.
Mm-hmm.
But my goodness, Tim, when you look at the PQC algorithms, they're unbelievably complex.
Yeah.
So the chance of blind spots goes up.
Right. Yeah. Yeah. And not only has it not been patted on for so long, but these are relatively esoteric branches of mathematics, which means that the number of really trained experts that you have is on the low side.
Suggests there's room for AI there, just like Michaela Muska said.
Good point. All right.
Anyway, Tim, that's it.
All right. Love it.
Thanks, Tim.